Well, the whole business started actually over a discussion at coffee time, and it was the custom, and still is in fact the custom, to have coffee in the coffee room down in the physics department at about 11 o'clock. And we started discussing, as to say, myself, Peter Grinnell, a student at the time, and Alan Garraway, and we started discussing where we should go next. Basically, we'd got all these very nice results using fluorine resonance, and we were really looking for chemical shift properties of certain materials, certain solids, and so on. But then when we had exhausted all the materials that were readily available, we wondered what we should do next. And the conversation seemed to turn around to thinking, well, we've got this very nice line narrowing. We can narrow lines, in the case of calcium fluoride, down to something like 1 or 2 hertz line width. Could we use that for anything? I mean, if we could apply a gradient to it, we could study the atomic structure. And it was at that point that I suggested that maybe, that's what we should do. And Alan Garraway was a bit sceptical, but Peter Grinnell, who was more amenable to suggestion because he was, after all, a student approaching his 3rd year, he grabbed that, and we worked together on it. I did some calculations, and the whole subject started. This was in 1972. It led to the idea that perhaps what we should do initially was to create a sort of model lattice, which was made of layers of camphor in our case, and this was sandwiched together to form a discrete structure. And then by using line narrowing and a field gradient, we could actually see the structure. So we simply had made, if you like, a simple crystal, not really a crystal, but ostensibly something which had structure in it. And then we could look at that structure in a magnetic field gradient. So we had several things working on those very, very early experiments: line narrowing, the application of a magnetic field gradient, and the observation of structure. When the special or specialized colloque Ampere was organized, Raymond Andrew was invited as the opening lecturer, and I was the number 2. So he went on stage first and gave a talk on his spinning solids work, and then I followed with my so-called NMR diffraction work and showed these results, and that created quite a stir in the conference. So much so, in fact, that there were questions afterwards on my paper, and one of the people that raised the question was John Waugh. And he made the point that he thought he'd seen something very similar published in Nature very recently. And I hadn't seen it. I actually didn't really read Nature regularly. And so he said he thought he'd seen something very similar. Could I comment on it? And I said that I hadn't seen it. I asked him actually whether it was connected with imaging in solids, and he said he didn't think it was. It was a liquid system that had been looked at. So when I got back to Nottingham, I went straight to the library, looked up the relevant article, and there was Paul Lauterbach's work, and it had been published about 2 or 3 months earlier on his idea of NMR zoogmatography, as he called it. And what he had actually observed was a crude image of 2 test tubes, and he had no special algorithm for producing the image. He'd done it all by hand. But nevertheless, it was, the first indication that you could do imaging. But it was done by a completely different technique to the way we were working. So the main difference is mathematical in a sense, because Paul was trying to produce images in real space, and the images that I was working on were brought about through K-space. Now, K-space is reciprocal lattice space, and without going into more mathematical detail, I think I'll leave it there. But it seemed to me much simpler to work in K-space rather than real space.